Hello. This brief video is meant to provide a motivation for the analysis of variance test. More specifically, why do we actually need this different type of instrument in statistical analyses? Before delving further into the theory and the mathematics around ANOVA, I'd like to examine a context for an ANOVA. In this context, actually, we'll begin to highlight some of the limitations of the t-test. In a previous example, we saw the teacher-student-teacher issue, where a teacher had a student-teacher come into class, and the teacher wanted to try a quote-unquote experiment and had the student-teacher do one activity with a random set of the students, and the teacher did something else. And of course, the threat to validity there was whether it was the treatment that had the effect, showing the difference between the two randomly selected groups, or if it was the fact that the teacher and the student-teacher are different in ability levels. One way around this threat to validity is what we call design 6B, or the variability in the execution of the treatment. So it's important to remember here that empiricism is built on replicability in the natural sciences or representativeness in the social sciences. In fact, it turns out that exact replication in the social sciences may actually introduce a new threat to validity. Variation introduces chance and begins to undermine the plausibility of alternative explanations for the treatment effect. So in this case, let's not train one teacher for the treatment, but we'll actually train three. So we have similar treatments with minor variations. Again, we have random selections. We have 4 groups. 3 are treated, but in slightly different ways. And then there's one control group. So we have 4 science classes. Students have been randomly assigned to each class before the start of term, so we could assume random assignment. There's one control group. It's been assigned homework, but there's no study workbook provided. The other 3 groups are assigned homework and provided study workbooks, but each group is given a slightly different study workbook. So the desired results are to see that the control group is different from the 3 experimental groups, but that within the 3 experimental groups, there's really not much difference. Now, the naive approach, again, naive in this context, not being a negative thing, just the surface understanding, the naive approach is to run pairwise t-tests and to ask if we actually see a difference. So we could look at the control group compared to the other 3 groups, and then within the 3 treatment groups, we could compare them to each other. And here are the results of such a set of paired comparisons. We notice that when we compare treatment 1 to the control, we get a statistically significant value of 0.046 if we have a cutoff of 0.05, but if we're using a more strict cutoff of 0.02 for our significance level, that may not be considered significantly different. Whereas the treatment for group 2 compared to the control and group 3 compared to the control appear to be statistically significant under most measures. Alternatively, when we look at the 3 treatment groups compared to each other, we see that treatment 1 compared to 2 and treatment 2 compared to 3 appear not to be statistically significantly different from each other, but there may be a chance that the differences between group 1 and group 3 are statistically significant. Now, this is where we need to actually examine the curse of probability. This is when we have repeated t-tests. Again, remember, the p-value is the probability of making a type 1 error, which is rejecting something that is true, i.e. rejecting the null, when in truth, the null is actually the true. Multiple experiments compound the likelihood of making at least one type 1 error rate, assuming independence, which is a kind of a sketchy assumption in this case. The chance of an error for each trial is 0.05. That means 5% of the time, the null hypothesis would be true, and by random chance, we would obtain a result that would have us reject that. So the chance of being correct in each trial is about 95% of the time. The chance of being correct in all 6 trials would be 0.95 raised to the 6th power, or about 73.5%. So the flip side of all 6 trials being correct is that at least one error was made in the 6 tries. That's 1 minus 73.5%, or 26.5%, which is a greater than 1 in 4 chance. So there's a greater than 1 in 4 chance that we actually made at least one type 1 error in our 6 measurements. This is often compared to what we call the birthday problem, which is an interesting exercise in probability where you examine groups of people that might share a birthday. And the surprising result is that if you have only 5 people in a room, there's only about a 2.7% chance that 2 of them might share a birthday. By the time you get to 15 people, there's about a 1 in 4 chance that 2 people share a birthday. And by the time you get to 30 people, there's over a 70% chance that 2 people will randomly share the same birthday. This is related to the idea of the experiment-wise error rate. So we refer to the alpha PC as the per comparison or per contrast type 1 error rate, and alpha EW is the experiment-wise or family-wise type 1 error rate. the chance of making a mistake for at least one of the comparisons. Ideally, when you decrease the alpha PC, you also reduce the alpha EW. If in our previous example, we'd had a per comparison significance level of 0.05 divided by 6, then generally speaking, our overall experiment-wise type 1 error rate would have been the desired 0.05. There are other protocols that can be used to control for experiment-wise error rate, and we'll revisit a number of these when we look at multiple comparison protocols. But now we want to think of the ANOVA as what we would consider an omnibus test, where the omnibus is a master test. All I need to do is run this one test to ask if there is any difference amongst the variables that I'm actually interested in. So in the previous example, the context indicated multiple different groups, while the claim was that some groups were different from others. Most generally, at least one group in the population mean does not equal the other. The opposite of this is that all the groups would actually be the same. Looking at this from the ANOVA hypothesis, the claim is that at least one pair of group means is different, the opposite being that all group means are equal. We hope to disprove the latter, and then we prove the former. Written as hypotheses, the null hypothesis would be that the average for group 1 is equal to the average group 2, is equal to the average group 3 for all of the groups. The alternative of that is that at least one of the group means are not equal. And here are the results when we actually do the ANOVA for the data for our final exams for the 4 groups that we were just looking at. The F ratio, which again we'll elaborate on later what that actually measures, the F ratio for comparing the 4 groups suggests that it would not have occurred by chance if all group means were equal, a significance level here of 0.001. Alternatively, if I only to look at the 3 treatment groups, the 3 groups that use the workbook, the chance of seeing the F ratio here of about 2.4 and change actually occurs about 10% of the time. So it's likely that what we're seeing could be attributed to chance, meaning the 3 treatment workbook groups actually have the same average. And this appears to give us the desired result, where we have a treatment effect, which is essentially the use of these extra workbooks. Thank you for listening.